Next, let's see the Joule-Thomson effect. The Joule-Thomson effect is the temperature change caused by an isentropic change in pressure. As gas expands from P1 to P2 through a throttle valve, the temperature drops. As shown in the figure, gas is continuously provided from the throttle valve's left side. As a result, both sides' pressure stay unchanged, while the gas volumes on the left and the right sides of the throttle are expressed as V1 and V2. The work done by the gas is calculated as follows. This relationship. If there is no heat input during the process, this work is done by consuming the gas's internal energy. As a result, the gas's temperature drops as the internal energy decreases. The internal energy of both sides are denoted by E1 and E2 respectively. We get the following relationship by applying the first law of thermodynamics, which is expressed by this equation. In the adiabatic process, no heat input, so Q should be 0. And heat is sum of work done by gas and change in the internal energy. So from this equation we can have this relationship. So according to this equation, the enthalpy is given by sum of energy plus PV is conserved during the throttle process. As a result, we can see that the Joule-Thomson process is isentropic. So gas is continuously supplied from left, and this gases are penetrated through the throttle. So at this size, pressure is P1, and here P2, and temperature T1 and T2 is here. So no heat input is provided, and so this process is done in the adiabatic process. So enthalpy is conserved in this process. So this throttle can be consisted of the partially open valve or porous block. In addition, the first law of thermodynamics is written as this equation. The relationship of differentiation of E plus PV is the enthalpy, differential of enthalpy, and you can have this relation. The differential of enthalpy is given by this equation. Can we calculate from the equation above? The following is rearrangement of this relationship. So entropy is the function of temperature and pressure, So total differential of the entropy is entropy S ds dt dt and ds dp dp. So we have this equation for this part, and we can have this term here, and specific heat is defined by this term. So you can have Cp dt, and we can arrange this term. So the differential of the entropy is given by this relationship. Since this enthalpy in the Joule-Thomson process is conserved, so dH should be 0. So you can get the Joule-Thomson coefficient as differential of the temperature as function of the pressure, or is defined as temperature coefficient. So using this relationship here, we can get the alpha by this equation. So for this we used Maxwell relationship. This relationship we use here. So the Joule-Thomson coefficient alpha jt becomes either positive or negative depending on the relative magnitude of two terms. In this equation, this term minus v. So alpha jt becomes either positive or negative depending on the relative magnitude of the two terms, this term and volume. Okay. If alpha jt is positive, the temperature of the gas decreases as the gas expands. Gas expands means the gas pressure is lowered. However, alpha jt is negative. The temperature of the gas rises as it expands. So we can have a cooling effect. We can see from a publication for alpha jt that in the Joule-Thomson process with an ideal gas, there is no temperature reduction effect, since dV over dt is given by V over T for ideal gas. So if we put this here, then alpha jt equals 0. So we can have any temperature reduction effect for ideal gas in the Joule-Thomson process. Ideal gas is a gas with low density. The density of the gas increases during liquefaction, hence it should be considered a real gas. So the Joule-Thomson coefficient is calculated using the van der Waals equation for real gas as follows, and we can get this relationship. If the volume is large, V is large, then the relationship can be rewritten as this equation. So this cancel, so we can have this equation. This equation expresses that alpha jt is greater than 0 for this term is larger than 1, and alpha jt is negative for this condition. In the process, in the pressure versus temperature diagram here, several curves for the isenthalpic process of real gas are shown. So there is the isenthalpic process for real gas. In this case, the inversion curve, this inversion curve is a line, this blue line indicates the inversion curve. So this inversion curve is a line that connects the points when the sign of alpha stage changes. You can see here, for example, H1 as isenthalpic curve, right side, this is the point on the inversion curve. On the right side, alpha jt is negative, the slope is negative, and on the left side, slope is positive. So slope is change from positive to negative at this point. So that is if we connect these lines, connect these points, if we connect these points, then we can have a line. This is called the inversion curve. So on the left side of the inversion curve here, this reason, alpha jt is positive, so the slope is positive. On the right side of the inversion curve, alpha jt is negative, so slope is negative. As a result, the starting pressure and the temperature of gas for liquefaction via the Joule-Thomson process should be on the left-hand side of the inversion curve, because at this reason, alpha jt is positive, so we can have the cooling effect. But this reason, alpha jt is negative, so we cannot have the cooling effect. So the starting pressure and temperature of gas for liquefaction via Joule-Thomson process should be on the left side of the inversion curve. Otherwise, the Joule-Thomson process will not be able to liquefy the gas. At each isenthalpic curve, the inversion temperature represents the point where alpha jt equals 0. So here we have this. No, here we have this relation. Okay, the inversion temperature at the 0 pressure. So the 0 pressure is here, right? So this point. So the inversion temperature at the 0 pressure, which is denoted by Ti maximum from alpha jt equals 0, indicated in the figure, is defined as the maximum inversion temperature of the certain curve, a certain gas. So Ti max represents the maximum inversion temperature of a certain gas. Okay. So the starting temperature of the Joule-Thomson process should be lower than the maximum inversion temperature of for liquefying gas. So if we want to liquefy a certain gas, then the starting point of the Joule-Thomson pressure should be lower than this maximum immersion temperature. Otherwise, the gas cannot be liquefied. Now let's look at why the real gas in the Joule-Thomson process has gas temperature reduction effect. In terms of NOV, so density of the particle, the equation for the state of real gas has become, we can write the equation of state for real gas in this way. Here, P2, P3 are the virial coefficients. As can be seen, for an ideal gas, all of the virial coefficients are 0, so it is 0, so we have PV equal NKT. So that is the equation of the states for the ideal gas. And if NOV is not too great, then we can omit the terms larger than these terms can be omitted. So we can omit this above terms for the relatively small NOV. So we can have the following equation from here. The intermolecular interaction in a gas is commonly explained using Reynolds-Jones potential, as shown in this figure. The van der Waals attraction force is exerted when the separation between gas molecules is larger than the size of molecules. So this is the actually size of molecules for in this region. When the separation between the gas molecules is larger than the size of the molecules at this region, van der Waals attraction force, that's attraction negative, so attraction force is exerted. However, if the intermolecular distance between gas molecules is short, so at this region, then repulsive force is exerted. So this is the Reynolds-Jones potential usually used for the intermolecular interaction. Since the kinetic energy of gas molecules is low at low temperature and the intermolecular distance is large, and attraction force is exerted between molecules. As a result, the gas pressure drops slightly below that of the ideal gas because the attraction between gas molecules is larger. Then the gas pressure is slightly reduced by this intermolecular attraction. To meet this requirement, P2 must be negative as seen in this equation. So P2 must be negative because pressure is reduced in the intermolecular attraction process. So the P2 is slightly negative, right? The intermolecular force increases as temperature decreases, resulting in a great reduction in pressure. As a result, as temperature decreases, B2 decreases linearly. On the other hand, at high pressure, high temperature, the gas molecules become active and frequently collide with one another. At this high temperature, the gas pressure exceeds that of idle gas because molecules collide frequently, so B2 becomes positive. This term, is smaller than order of 1, so as a result, the volume V in this term can be replaced with this equation, this term, which is observed from state of equation for idle gas. So PV equal NKT, so we can have this term like this. So if we put this here, the term can be written this way. So if we put this here, so if we put this expression into here, then we can obtain this relationship. So volume can be written by this equation. Now applying this expression into here, that's alpha JT. So we can obtain dV dt using this relationship. Then we can have the Joule-Thomson coefficient like this equation. So that is the Joule-Thomson coefficient for the Joule-Thomson process. Since B2 Peeler coefficient increases as temperature rises, so this term becomes positive. The sign of B2, on the other hand, is temperature dependent. We already saw that. So B2 is negative at low temperature, hence alpha JT becomes positive. So at low temperature, B2 was negative, right? So alpha JT, B2 is negative, right? So this term is positive. And low temperature of B2 is negative, so we have alpha JT positive. So the Joule-Thomson process can therefore lower the gas temperature. On the other hand, at high temperatures, B2 becomes positive. So positive. Then only when the this term exceeds B2, this term, does alpha JT become positive. So the other way, alpha JT becomes negative. So in order for alpha JT to be positive, this term should be larger than this B2. Okay. So the inversion curve is defined as temperature at which the sign of alpha JT changes. So this for this isenthalpic process, so that at that point alpha JT change its sign from positive to negative. So if we connect these points, then we can have inversion curve of that gas and the immersion temperature at zero pressure gives the maximum immersion temperature. So if we want to liquefy a certain gas, we have to start the Joule-Thomson process below this maximum immersion temperature. Otherwise, we cannot liquefy the gas. The gas with the lowest maximum immersion temperature has a lower boiling point, as can be seen in this table. So helium has the maximum immersion temperature is lowest, and helium has lowest boiling point among all gases. It is therefore difficult to liquefy a gas having a lower boiling point. So boiling point is 4.2 Kelvin for helium, so that's the lowest boiling point. The maximum immersion temperature can be used to classify gases. Okay, you can see here, except for helium, hydrogen, and neon, all gases have maximum immersion temperature above room temperature. You can see here maximum immersion temperature for other gases: nitrogen, air, CO, argon, oxygen, methane, and ammonia all has the immersion temperature above room temperature. Okay, except these three gases: helium, hydrogen, neon. Its maximum immersion temperature is below room temperature. Okay. As a result, these gases can only be liquefied using a Joule-Thomson valve. So these gases, yes, these gases has a maximum immersion temperature larger than room temperature. So for these gases, we can liquefy these gases only with the Joule-Thomson valve. However, for these three gases, before we can use a Joule-Thomson valve to liquefy helium, hydrogen, or neon, these three gases, we must first utilize a series of expansion engines to reduce the temperature below the maximum immersion temperature. Because the maximum immersion temperature for these gases is lower than the room temperature. So we have the first temperature of gases using the expansion engine below this maximum immersion temperature. Then we can use the Joule-Thomson valve to liquefy the gases. Both expansion engines and the Joule-Thomson valve are necessary to liquefy these gases. So for these gases, we can liquefy these gases only with the Joule-Thomson valve. But these three gases, we have to use expansion engine to lower the gas temperature below their maximum immersion temperature. Then we can use the Joule-Thomson valve to liquefy those gases. Okay. A Joule-Thomson process results in a very small temperature drop, typically a few tenths of the degree per 1 atm pressure change. Okay, so very small change in temperature. However, subsequent procedures can drop the gas temperature below the liquefaction temperature. The temperature drop induced by an expansion engine, on the other hand, is significantly larger than that caused by a Joule-Thomson valve. When there is liquid in the expansion engine, however, it does not work properly. So as a result, the expansion engine is commonly employed to reduce the temperature of gas below the inversion temperature. Liquid nitrogen is also used to pre-cool the helium gas before it enters expansion engines of helium liquefier. The maximum inversion temperature of helium is very small, 4.2 Kelvin, so we have to use the nitrogen to pre-cool the helium gas before entering to the expansion engine. Okay. A liquefier is made up of 4 key components: the compressor, heat exchanger, expansion engine, and Joule-Thomson valve are all parts of this system. The highly pressurized gas should be supplied to the expansion engine or Joule-Thomson valve. The compressor is used to pressurize the gas for this purpose. The temperature of the gas entering the low temperature region can be reduced by the gas returning to the compressor from low temperature region. So these gases come into contact with each other due to heat exchange. A Joule-Thomson valve liquefies the gas once it has been cooled below inversion temperature by expansion engines. The unliquefied gas returns to the compressor where the liquefaction cycle is repeated. It cools the gas coming down to the Joule-Thomson valve as it returns to the compressor via heat exchange. Now let's see the practical liquefier. First, let's see the Linde-Hampson liquefier. We already discussed that all gases except helium, hydrogen, and neon have the maximum inversion temperature higher than the room temperature. So we can liquefy those gases by using only a Joule-Thomson valve. So all gases, with the exception of helium, hydrogen, and neon, can be liquefied by means of the Joule-Thomson valve only. Okay. The figure below shows the most basic Linde-Hampson liquefier. It has one heat exchanger and a Joule-Thomson valve. Heat exchange is used to cool down the gas from compressor to the Joule-Thomson valve by exchanging heat with the gases from the container, which is very cold. So these gases temperature can be lowered by heat exchange with the cold gas from the container. Okay. So by exchanging heat with unliquefied cold gas from the liquid container, see, the gas from the compressor this way is cooled. Okay. So that's why we use this heat exchange. The liquefaction process is also depicted on the temperature entropy graph here. I see the process of liquefaction. By compression, the gas is pressurized 1 to 2. So this curve is isobaric curve. So gas enters to the compressor and then and pressurized and coming from the compressor and enter to the heat exchange. Due to the function of the heat exchange, the gas temperature is lowered to 3 here, and then by action of the Joule-Thomson valve, the gases enter into the two-phase region. So some of the gases become liquid, and other gases is unliquefied. This unliquefied cold gases coming from the container and go back to the compressor here. So the unliquefied cold gas is going to the compressor and then the liquefaction process is repeated and cycled. Okay? So in this way, the gas can be liquefied. So this simple Linde-Hampson liquefier is used for all gases except helium, hydrogen, neon. These gases maximum involution temperature is lower than the room temperature, so we have to use for this gas liquefaction, we have to use the heat expansion engines. So this figure shows the Collins helium liquefaction system. This one, and this is entropy graph. The entropy figure represents two isobaric curves. One, this two black lines. A compressor pressurized the gas from 1 to 2. Okay. And two expansion engines and the heat exchanges drop the gas temperature to 0.5 here. Then a Joule-Thomson valve then allows the gas to enter the two-phase region 6, and the sum of gases are liquefied, and remaining unliquefied gas so coming from the container to the compressor again. Okay. The gas that does not liquefy in the two-phase region returns to the compressor, where the liquefaction cycle is repeated. Okay. So let's see the entropy diagram in details. So 1 to 2 is compressed gases, and by the function of the heat exchange, the gas temperature is lowered to 3. Okay. And another heat exchange here, due to the action of this heat exchange, the gas temperature is lowered even further, lowered, therefore, and the last heat exchange, so we can load the temperature even rho 5, and then due to the Joule-Thomson valve, the gas enters into the two-phase regions, and the sum of gas is liquefied, and unliquefied gas go back to the compressor. So this gas is going to the compressor is cold. Okay, this blue line cold, and the gas from the compressor is hotter. So between these two gases, heat can be exchanged. So the gas from compressor, the temperature is lowered by this heat exchange. So this figure, entropy figure, shows these processes. The Collins liquefaction system is depicted in figure. Two expansion engines, E1 and E2, and a Joule-Thomson valve are used in this system. Liquid nitrogen is used to cool the gas before it enters the first expansion engine. So liquid nitrogen is used as a pre-cooler. This liquefaction system has 4 heat exchangers, as can be seen here. So using these kinds of liquefaction system, we can liquefy all gases. So I can summarize again, except helium, hydrogen, and neon, all other gases have the maximum inversion temperature rather than the room temperature. So we can liquefy those gases by using only a Joule-Thomson valve. However, the maximum inversion temperature of helium, hydrogen, and neon is lower than the room temperature. So we have to lower the gas temperature below this maximum inversion temperature. So we have to use the expansion engine to lower the gas's temperature. So we have to use the expansion engine to lower the temperature below the maximum temperature or maximum inversion temperature of this hydrogen, helium, and the neon gases. Then finally, by the action of the Joule-Thomson valve, the gases can be liquefied.